Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel, so I request you to visit my channel regularly and repeatedly and watch all the videos available there, so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish, so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier, and when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am going to describe about yet another very important aspect of all submerged arc furnace operations, and the title of this presentation is Measurement and Control of Arcing in Submerged Arc Furnaces. So this topic mainly describes the details about how to measure and control the arcing in a submerged arc furnace and what is its importance, how it affects the overall furnace operation and electrode operation. So please do watch this video very carefully and sincerely. And before proceeding to this video, I would like to all of you to view and observe the next video in the next slide. As you have seen and observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So, my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always. I hope my message in the previous slide video is very much clear to you all. So now let us start this video. To start with, let's have the introduction. The extent and type of arcing that takes place in a ferroalloy furnace is directly related to the metallurgy of the process. Recently, with the advent of powerful processors in personal computers, it has become possible to study the detailed behavior of the electrical circuit in a submerged arc furnace in real time. For this purpose, a system known as the arc monitor or ArcMon has been developed at Mintech, and process studies have now been done on a number of industrial furnaces using this equipment. The purpose of this presentation is to briefly compare the results obtained to date on furnaces producing silicon, ferrosilicon 75% and charged chrome. A resistor is inherently a linear circuit element in that the instantaneous voltage across it is proportional to the instantaneous current. On the other hand, an arc is a non-linear circuit element and consequently distorts the sinusoids of the AC currents flowing around the circuit of the furnace. This distortion of the waveforms thus provides information about the behavior of the arcs in the furnace and hence can quantify the extent of the arcing as opposed to the resistive conduction in the furnace. The inputs to the ArcMon are the AC signals from the high voltage lines on the primary side of the furnace transformers. The transformer tag positions are also monitored in order to relate these primary side measurements to the secondary side. There are thus no connections on the secondary side, and in particular there are no connections to the furnace hearth. The ArcMon then uses a recursive estimator to fit the circuit parameters to these waveforms. To accommodate the inherently non-linear nature of the arc, the estimator is based in the time domain, that is, it does not use the frequency domain and hence does not involve the use of harmonics. Also, the ArcMon runs the recursive estimator in real time and so tracks the variations in the circuit parameters continually while the furnace is running. Now let us discuss about the power circuit of the furnace. The equivalent circuit of the furnace is used for the ArcMon is shown in figure 1 in the next coming slide. In brief, it consists of a star circuit with each individual electrode in the furnace corresponding to one of the branches of this star. Each branch then consists of a magnetic inductor, an arc and a basic burden resistor, all in series. To distinguish between arcing and resistive conduction, an electrical model of an arc is needed. In the ArcMon, a linearized form of Cassie's model has been used. This would seem to provide a reasonably good fit to the observed waveforms. The burden resistors are modeled by Ohm's law. So this is the equivalent circuit of furnace. This shows how the conduction through the burden can be split into an arcing component and a purely resistive component in series. The equivalent circuit shown here excludes the delta elements that model the pulses in the transformer magnetization currents. The arc mount can also accommodate a stinger electrode if needed, as indicated by the dotted branch of the circuit. You can pause the video and observe the figures and its elements. Okay. So now let us discuss about initial results on the silicon type furnaces. In brief, these results can be summarized as follows. First, the linearized form of Cassie's model was used for the arc, and the resulting waveforms generated by the circuit equations were a good match to the actual waveforms even under extreme conditions. Second, there is a slight but also continuously varying asymmetry between the forward and reverse conduction under each electrode. This produces a partial rectification effect and so gives rise to varying DC components in the currents. These DC components affect the magnetization of the steel core in each of the transformers, driving the operation of the core over the knee of the magnetization curve and into the region of magnetic saturation. The waveforms of the magnetization current then develops a short, sharp pulse in every cycle around the point where the magnetization saturates. Because each transformer feeds two electrodes in the knapsack configuration, these pulses get superimposed on the primary currents of the two phases associated with that transformer, but not on the current in the remaining third line. These delta current pulses vary sporadically and are normally fairly small, but at times may rise to exceedingly high levels. These pulses are identified, quantified and compensated for as part of the estimation of the circuit parameters. The extent of arcing in a silicon furnace is significant. Typically, the power that is dissipated in the arcs is of the order of 20 to 60% of the total power delivered to the furnace. Fourth, the extent of arcing also varies continually. Although much of these fluctuations seems to be simply random, there are certain mechanisms evident. In particular, movement of an electrode hoist has a direct and immediate effect on the corresponding arc voltage. The basic burden resistance is not immediately affected by the hoist movement but may respond slightly after several minutes. The extent of arcing is also influenced by the feeling, raveling and tapping of the furnace. One can intentionally manipulate these factors to influence the extent of arcing. Now let us observe the comparison of chromium type and silicon type furnaces. To start with, let us first have a comparison of waveforms. Figure 2 shows an example of waveforms from a ferrosilicon furnace, while figure 3 shows a corresponding example from a charged chrome furnace. In each of these figures, the waveforms of the three electrode currents are shown on the upper axis, while the lower axis show the derivatives of these current with respect to time, that is di by dt. These waveforms are typical of normal operation on both types of furnaces. In both these figures, the waveforms of the currents appear to be almost pure mains frequency sinusoids, but the derivatives enhance and hence reveal significant distortions around the basic sinusoids. The arcs in the circuit are the source of these distortions. In the process of differentiating a sinusoidal waveform, a phase shift of pi by 2 radians, that is equal to 90 degrees, is produced, that is d by dx sin x is equal to cos x is equal to sin x plus pi by 2. And so the peaks of each di by dt waveform synchronize with the zero crossings of the corresponding current waveform. Thus, the slight dent in each peak of the di by dt is associated with the arc in that phase being restarted after the zero crossing of its current. Hence, the magnitude of the dent in the peak of the di by dt is a visual indication of the extent of arcing in that phase. So this is the figure 2, which shows waveforms from a 75% ferrosilicon furnace. This figure shows the waveforms of the electrode currents on the upper set of axes and the derivatives, that is di by dt, of these currents on the lower set of axes. These waveforms are from a ferrosilicon furnace dissipating around 25 to 30 megawatt. The presence of arcing in the furnace reveals itself by the distortion of particularly the di by dt waveforms. In this example, a small amount of delta current pulsing, see the text, is also occurring between electrode 2 and electrode 3 as encircled. So I have already explained these two waveforms figures. So let's move on. And this is the figure 3, waveforms from a charged chrome furnace. These waveforms are from a charged chrome furnace dissipating about 45 to 50 megawatt. In comparison with figure 2, it is very evident that the distortion of the di by dt waveforms here is significantly less than in the ferrosilicon furnace. I have already explained this. I hope it is very much clear to you all. My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here, specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on. When comparing figures 2 and 3 in this way, it is very evident that there is considerably more arcing in the ferrosilicon furnace than in the charged chrome furnace. Furthermore, in figure 2, a small amount of delta current pulsing is evident. In this particular example, it can be seen on the di by dt waveforms of electrode 2 and 3 as small steep jumps as encircled in the figure. The presence of this delta current pulsing indicates that asymmetrical conduction in the arcs also takes place in the ferrosilicon furnaces, much as it was found to do in the silicon furnaces. The ArcMon has detected this delta current pulsing in charged chrome furnaces as well, but with somewhat smaller magnitudes that are not as easily seen on the waveforms. Now let us have a comparison of the arc voltage magnitudes, that is parameter VA. The waveform of the voltage across an arc in a furnace is normally a slightly skewed square wave with rounded edges. When Cassie's model is used to describe the arc, the parameter VA is approximately the magnitude of this square wave. In some extreme cases, particularly where the operation is very unbalanced, the arc waveform may become distorted, but VA continues to provide a measure of the magnitude of the arc. Figure 4 and 5 show typical examples of the evolution of VA over a period of 24 hours, with figure 4 for ferrosilicon and figure 5 for charged chrome, which are described in the coming slides. For clarity, only one of the faces from the corresponding furnace is shown in each of these two figures. Also, the ArcMon estimator has a lower limit that prevents the estimate of VA going to zero, which is why the traces on the graphs never actually touch the horizontal axis. Again, it is clearly evident that there is far less arcing in the charged chrome furnace than in the ferrosilicon furnace. So this is the figure 4. I have just explained it. You can pause the video and observe its details. And this is the figure 5. I have just also explained this. Okay, moving ahead. In the case of ferrosilicon, that is in figure 4, there are a few short periods where VA drops to virtually zero, but most of the time VA lies within a band of about 20 to 50 volts. There is also a significant amount of random noise on this signal. This is fairly similar to a silicon furnace. In the case of charged chrome, that is in figure 5, the arcing tends to occur in bursts. These bursts are associated with the tapping of the metal and slag from the furnace. In between these bursts, the arc voltage is virtually zero. The extent of arcing during these bursts can vary, normally rising to peaks of about 10 to 12 volts but occasionally rising much higher. Now let us have a comparison of the arc power fractions. The arc mole unit is also able to calculate the amount of power dissipated in each of the arcs and each of the resistors of the equivalent circuit of a furnace. Through this, it is able to calculate the fraction of the total power to the furnace that is dissipated in the arcs, which we will here term as the arc power fraction. This is another measure that can be used to compare the amount of arcing between the different processes. The usefulness of this arc power fraction as a measurement as opposed to the individual VA or RBB signals arises from the fact that it is a single quantity for the furnace as a whole and it is independent of the power or current levels in the furnace. It also has a direct metallurgical relevance as to how the energy dissipation is split between the various zones within the burden of the furnace. In this way, figure 6 shows a typical arc power fraction for a ferrosilicon furnace over 24 hours and figure 7 shows the same for a charged chrome furnace in the coming slides. Perhaps not surprisingly, the magnitude of the arc power fraction in the ferrosilicon furnace is similar to that in the silicon furnace, that is, it is of the order of 20 to 60%. In the case of charged chrome, the arc fraction is much lower and comes in bursts that follow the tapping of the furnace, similar to the trend of the VA for the charged chrome furnaces as shown in figure 5 above. So let us have a discussion, some points discussion. It is very evident from figures 2 to 7 that normally there is significantly less arcing in a charged chrome furnace than in a ferrosilicon furnace. Furthermore, in a charged chrome furnace, there is a burst of increased arcing for about 1 hour after each tap, whereas in a ferrosilicon furnace, this behavior is not readily observed. Ferrosilicon and silicon furnaces, let us have some points in detail. The amount of arcing in a ferrosilicon furnace is similar to the amount about 20 to 60% for a silicon furnace. The apparently random way in which the arc power fraction varies is also similar. Furthermore, the response to an electrode being moved is similar as well. Metallurgically, the ferrosilicon process is similar to the silicon process in that there is a crater around the tip of each electrode in which the arc is located. There is not normally any significant slag layer. It is not surprising then that both types of furnace behave similarly from the perspective of arcing and related electrical behavior. While the arcing takes place in the crater zone, the resistive power dissipation presumably takes place elsewhere within the burden of the furnace. The extent to which the power is split between these two zones has implications for the metallurgy of the process and hence the efficiency of the furnace. Now let us discuss some points of charged chrome furnaces. Charged chrome furnaces in the industry can vary from a typically low resistance operation to a relatively high resistance operation. The purpose of having a high resistance operation is to facilitate an increase in power delivery within the same electrical constraints for a given furnace installation. Levels of arcing that were observed many years ago on furnaces with lower resistances were significantly more than the levels observed in the present study, which has been done to date on furnaces with higher resistances. The charge chrome process has a significant quantity of slag in the furnace. Floating on top of this slag layer, there is reportedly a carbon bed, which is also called a coke bed. Some mixing between the slag and this carbon bed presumably occurs during normal operation, although this is not evident from post-mortem studies. Arcing is not likely to occur much in conjunction with a slag layer, but it can be expected to occur more easily within a coke bed and between a coke bed and the tip of an electrode. Therefore, the low amount of arcing measured by the arcmon in the period preceding a tap is probably associated with the bulk of the carbon bed being located higher up in the furnace than the tips of the electrodes, so that the conduction takes place through a zone that contains predominantly slag. So this is the figure 6 which I have just explained earlier. You can pause the video and observe the things. And this is the figure 7 which I have also described. During the tap, as slag and metal are removed, cooler particulate material from the carbon bed and the raw materials descend in the furnace. The observed increase in the amount of arcing after tapping the furnace is probably associated with a significant portion of this particulate material entering the conduction zone beneath the electrodes. After the tap hole is closed, the smelting taking place in the furnace slowly increases the depth of this slag layer until after an hour or so, the carbon layer again rises above the level of the tips of the electrodes, and the amount of arcing decreases. Electrode tip breaks also leads to significantly higher levels of arcing for extended periods, often up to 1 to 2 days, until the electrode can be slipped sufficiently for the tip to return to its original position in the furnace. In this type of smelting process, higher temperatures in the reduction zone will enhance the reduction of the more refractory oxides, in particular that of silicon. This will increase the percentage of these elements in the final alloy that gets tapped. In particular, the percentage of silicon in the metal will increase. The extent of arcing does affect the temperature distribution in the reaction zone. Now let us have some discussion about arc voltages and arc lengths. Bowman has reviewed correlations between arc lengths and arc voltages in DC furnaces. In this case, the arc voltages around 20 to 50 volts correspond to arc lengths from a couple of millimeters up to about 100 millimeters. Although it is questionable as to what extent such correlations can be applied to AC furnaces, it seems reasonable to assume that they will not be too dissimilar. This would mean that the arc gaps in the craters beneath the tips of the electrodes in a ferrosilicon furnace would be typically up to about 100 millimeter long. This agrees with the changes that we have seen in the estimated VA when the corresponding electrode is moved. It also suggests that from the very low VA voltages that are observed in charged chrome furnaces, the arcing taking place in such furnaces is over very short lengths, probably little more than just adjacent conductive particles brushing past each other. So now let us discuss about use of arcing information in the control of the furnace. Clearly, the mode of electrical conduction in silicon and ferrosilicon furnace is very different from that in charged chrome furnaces, particularly in terms of arcing. Consequently, the approach to control these two types of process is somewhat different. So now let us discuss these effects in silicon and ferrosilicon furnaces. In the case of silicon and ferrosilicon, the movement of an electrode quickly and directly affects the arc-mon estimate of the corresponding VA parameter. Hence, VA can be controlled through the movement of the corresponding electrode. While it is possible to control an electrode's movement directly from VA, we have found it more practical to use a cascade arrangement in which the parameter from the arc-mon is used to modify the resistance set point of the Minstrel resistance controller, and the Minstrel's resistance control algorithm then adjusts the electrode position. Allowing the resistance set points to vary in this way can affect the power delivered to the furnace, causing variations both upwards as well as downwards. Such variations may temporarily affect the rate of production of alloy in the furnace, although they do tend to average out over longer periods. Consequently, it is necessary to constrain the allowable variation in the resistance set points that are sent to the minstrel. The extent of freedom within the constraints of the electrical operating region of the furnace plays an important part in this and varies from one furnace to another. One of the reasons for cascading the control onto the minstrel is that the minstrel then automatically maintains the overall operation within the safe electrical limits. The control of the electrodes, the raw materials, the tapping of the alloy from the furnace, as well as a number of other inputs into the operation of the furnace are all an integral part of the overall furnace operation. In a silicon or ferrosilicon furnace in particular, no one aspect can be viewed in isolation. Consequently, Mintech is currently investigating other approaches to the control that facilitates a more global perspective. The arc-mon contributes to this by providing unique information about the electrical side of the metallurgy which was not previously available. Now let us discuss the effects about charged chrome furnaces. Because the amount of arcing in the charged chrome furnace studied to date is very low for extended periods, here is no basis for any automatic control of the electrodes based on measurements of VA as described above for silicon and ferrosilicon furnaces. This is especially the case where the electrode hoists are allowed only limited movement. However, for other ferrochrome furnaces that have higher arc fractions, it may be possible to do such control. The sudden loss of an electrode tip in a large ferrochrome furnace with restricted electrode movement results in a sudden sustained increase in the level of arcing beneath the affected electrode. Information from the arc mount identifies this unequivocally. Arc mount parameters correlates with some of the furnace operating variables and can be used for predictions. The raw materials, particularly the carbon balance, affect the arc mount variable. Now let us have some conclusions which are based on these studies. First, in terms of electrical conduction, silicon and ferrosilicon furnaces behave very similarly but are very different from charged chrome furnaces. The modern charged chrome furnaces that were studied exhibited relatively low levels of arcing, but the extent of arcing increased for a short time after each tapping of the furnace. Electrode tip losses also increased the amount of arcing. This evidence suggests that the carbon bed is normally located relatively high up in the furnace so that most of the conduction takes place through slag, as there is only a relatively small quantity of carbonaceous reductant in the main conduction path beneath the electrodes. Third point, in silicon and ferrosilicon furnaces, the measurement of the arc voltage parameter, that is VA, can be used to control the electrode hoists. In the charged chrome furnaces studied, because VA is often virtually zero for a long periods of time, the use of this parameter for the automatic control of the electrodes is impractical, but the information may still be usable for controlling other process variables and for the detection of tip losses. The benefits of all these forms of control are presently still being studied and quantified. Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel, and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.